Today we are going to talk about how to compute the torsional potential of a molecule. So the torsional potential is a potential you are going to have if you rotate this angle. So that's the dihedral angle we are going to rotate. So an illustration for the dihedral angle is here. You can see that you have 3 bonds to define the dihedral angle. 1 bond, second bond, and a third bond. So it is angle between these 2 planes, and the beta plane is formed by these 2 bonds, and alpha plane is formed by these 2 bonds. So the dihedral angle is the angle between these 2 planes. So you are rotating this bond, so then you can change the angle between the 2 planes, alpha and beta. So this is a molecule we are going to study in this work. So today we are going to use the NWChem DFT program to do all the calculations. And we can first use the Avogadro software to build this molecule. The URL for the Avogadro software is here, and the URL for the NWChem software is here. So we are going to use the B3lib exchange correlation functional and the 6-31G star basis sets for all the calculations. NWChem is a Gaussian basis set DFT program, but of course NWChem can also do the plane wave DFT as well. But today we are going to use the Gaussian basis set based module in NWChem software. This is the input file for the NWChem program, and this is the geometry section. And you just give the XYZ coordinates in angstrom for all the atoms here. And we don't use any symmetry here, so we put symmetry equals to C1. This section is for the DFT simulation. You can see that we use a B3lib exchange correlation functional here. The basis set is defined in this section. And finally, we tell NWChem program we want to do the DFT simulation, and we also want to optimize the structure of the molecule. After the calculation in the log file, you will find this section, which gives you the relaxed positions of all the atoms. I also used the Vesta program to plot this molecule in this tutorial. And this is the relaxed geometry of the molecule. And in the meanwhile, I also labeled these atoms with the blue numbers. And those blue numbers represent the order of all the atoms in the structure. So you can see that this C1 is the first atom in the list, which is here. And this C2 is the second atom in the list, which is here. And this H hydrogen atom is the third atom in this list here. So these numbers for these atoms are very important because in the following discussions, we are going to use a MATLAB script to rotate this dihedral angle. And for that program, we are going to use those indexes to represent all the atoms. In the second step, with the relaxed geometry here, we want to check whether this C1, C2, C3, C4, these 3 bonds define a flat dihedral angle. So which means that the dihedral angle is 180 degree. But if you really calculate it, you will find that the relaxed structure from NWChem actually does not really give you the exact 180 degree for this C1, C2, C3, C4 dihedral angle. So I provide a MATLAB script here to calculate dihedral angle between 3 bonds. So the input from the user is that you need to give all the positions for all the atoms here to X variable. And then you define the 3 bonds in this way. You give the index of the 4 atoms that define 3 bonds to I, J, K, and L. You see that I equals 1 means that the first atom will be C1. J equals 2, the second term will be C2. K equals to 5 means that the third atom will be the carbon 3. The last is L equals to 7, which means that the fourth atom is a C4. So those are the 4 atoms, define 3 bonds here, here, and here to define the dihedral angle. So I also have this dihedral angle script to calculate dihedral angle for you. You just need to give the positions of all the atoms x here, and also the numbers for I, J, K, L. So the function dihedral angle is defined here. And after you evaluate this function, it's going to tell you the dihedral angle at this point of time is 179.21 degree, which is a little bit off from the 180 degree by 0.784415 degree. So which means that we want first to make a perfect flat angle for the C1, C2, C3, C4 dihedral angle by slightly rotate this part of the molecule by 0.784415 degree to make a perfect flat angle. In order to do that, I provide another MATLAB script for rotating part of the molecules. So here is the script. One input is the theta. So that is the how much angle you want to rotate. And we give negative 0.784415 divided by 180 times pi by convert degree to rad. And then the coordinates of all the atoms. You also tell the program what are the 4 atoms define the dihedral angle. And also you want to tell the program what are the atoms in this molecule you want to rotate. And here is 10, 5, 7, 9, 8. So let's take a look at of what atoms those are. So 10, atom 10 is this one. Because we are going to rotate this part of the molecule to make this C1, C2, C3, C4 dihedral angle to be totally flat. And so we have another atom which is 5, 9, 7, and 8. So that's why we put 10, 5, 7, 9, 8 here to the atom to rotate. I wrote a MATLAB script to rotate the atoms called rotate. All you need to do is to give the theta you want to rotate and x all the positions of all the atoms and j and k. So j and k are the 2 atoms which define the bond you are going to rotate with. So here the bond is the bond between C2 and C3. So this is the axis we are going to rotate against. So that's why we put a J2 and a K5 here. You also put a L here as well. Oh, sorry. So that's you put a J and a K here. You also put the index of all the atoms you want to rotate as well. So in the end, the program just gave you the new coordinates of all the atoms in the molecule has been rotated to the dihedral angle that you want. I also double check the dihedral angle in the end to make sure that I got the dihedral angle that I want. The rotate function is defined in here. And I looked up the reference here to write this script for rotating the atoms along an axis. So this is the new geometry of the molecule after the rotating. And you can double check with the dihedral angle function that we indeed get a 180-degree dihedral angle for this new geometry. Okay, so next we are going to use NWChem to calculate the energy of this molecule for a given dihedral angle. So this means that we are going to perform NWChem calculation, but with dihedral angle to be fixed. So NWChem has a very nice feature for doing this. You just need to add this geometry section, and in addition, this Z-chord section. You just need to, and also says that you want to define the torsion defined by the 4 atoms here, which is 1, 2, 5, 7, which are 1, 2, 5, 7 carbon atoms here. And you also tell NWChem you want to make the torsion to be constant with the keyword constant. So with this section here, NWChem is going to optimize the geometry of this molecule because we asked it to optimize it with DFT. But in the meanwhile, it's going to keep this dihedral angle between these 4 atoms to be fixed during the optimization. So this is the energy you will get in the end of the NWChem simulation, and the relaxed geometry is here, which can be found in the log file. Okay, for step 3, we are just going to rotate that dihedral angle to different angles, and then in the following parts of this tutorial, we are going to make the plot, which is the total energy of the molecule versus dihedral angle. And so the first thing we are going to do, we are going to slightly rotate the dihedral angle by 10 degrees to make it to be 170 degree, which means that we just need to set this theta to minus 10 degree, and the coordinates of all the atoms will still be the same as before. We also have the same definition for the IJKL to define the dihedral angle. And for the atoms to rotate, they are still the atoms with the index 10, 5, 7, 9, 8. And then I call this rotate function to rotate the right part of the molecule to make the dihedral angle to be 170 degree. You can also double check that you indeed get the correct dihedral angle in the end by calling the dihedral angle function. This is the rotated coordinates for all the atoms, and we are going to replace the geometry in NWChem with this rotated geometry of my molecule. And again, I'm going to fix the dihedral angle to 170 degree during optimization of my molecule by using this block here. In the end, for the step 4, you make a table and you list all the energies you got by changing the dihedral angle. You can make a plot looks like this, so shows you the energy profile versus the dihedral angle you have tested. So basically speaking that you have a barrier to rotate this bond, and then you have a potential well here as well. So this plot is very similar to this reference. Okay, so hopefully this tutorial is helpful to you for computing the dihedral angle in your molecules as well. Thank you for watching, and see you next time. Bye-bye.